Good afternoon. Let's begin lecture. I have a few comments for you about regrading the clicker items from exam 2. But before we do that, I'd like to just point out something that is amusing to me. The last quote of the month, or quote of the day for the month of October from Albert Einstein. He was kind of a wiseacre. And so a lot of stuff he said was really wise, and some of it was just kind of wise and off. The hardest thing to understand in the world is the income tax. And so I thought, yeah, I kind of agree with that. That's definitely true. Anyway, so starting Tuesday, we'll have, I don't know, somebody else for our quote of the day. About clicker items from exam 2. I sat down with a student after class, and we worked out Tuesday afternoon the fact that the blooper that I wrote into the exam had implications that I want to get squared away in a just manner. The blooper that I had was that I didn't print the value of G on planet X on the test itself. I did put it on the overhead display on the document cam, but some students did not catch that. And so a lot of students used 9.8, and they used it correctly, which is what we kind of figured out. And when I looked at the data files, the raw data files for the clicker session, last week, two sessions ago during the test, I looked at the raw data, and yep, there was quite a few people that were using 9.8 and doing it correctly. So I thought, I'll give these guys a break. And I'll grade it because it was my blooper. They were doing GPE and kinetic energy properly, many of them anyways, for 9.8. So I thought, all right, since it was my blooper, I'll reconcile it. I'll regrade everything. So some of you are in that position, and I'm going to regrade it, and hopefully some of you will see a few more points in the clicker portion. So what you should think right now is that your clicker, your exam 2 clicking score, that sub-score of the test, might change between now and Tuesday. All right, I'll try to get it done maybe tonight. All right, so the blooper doesn't affect the boxcar question, so that part of your grade will stay the same. And it doesn't affect the code question. And the code question I haven't graded yet at all, so that's going to have a third line below your exam 2 total. All right, so nobody's got that yet, and I got to try to do that this weekend as well. All right, now about these clicker questions, I scanned a handwritten solution that I actually did it again in good dark ink this morning when I woke up, and I was drinking coffee and doing this, and I scanned it. I did the boxcar questions first, and then I did the regular version of the Tweety Tomahawk Jam, and then I did the 9.8 meter per second squared version of Tweety Tomahawk Jam. And so I scanned it, and it's now available in the blurbs page in web courses. And it's a PDF, and you can download it and take a look at it and whatnot. Questions about this set of questions? Questions about questions? Okay, let's continue. I want to do a little recap of temperature concepts, kinetic energy concepts. Let's talk about it. Celsius. Now, we talked about Celsius. I'm not going to use a whole lot of it. I'm a theoretical astrophysicist, so I think in Kelvins, not Celsius. But like if you work for the Weather Channel, you're thinking Fahrenheit and Celsius, depending on what country you're broadcasting to, what country you're serving. But me, I'm Kelvin. But let's just review Celsius because it is kind of related to Kelvin. It's anchored to the boiling point of water, so I made that the top of my comparison chart. So we have two. Well, I can't really see it. Let's see if I move this forward a little bit. We have two. We have these two vertical bars, a pink one and a yellow one. One for Celsius, one for Kelvin, and the top of the temperature range that we're talking about is boiling point of water, 100 degrees Celsius, or 100 degrees Celsius. Then the other one is the freezing point of water. And a lot of our metric system and other measurement units are based on common everyday things like water, carbon, which is very abundant on the surface of Earth. That's used for a lot of atomic units. Between these two, by definition, the Celsius scale has 100 Celsius degrees. All right. Now, the Kelvin scale uses the same size degrees. It's part of the metric system. But its lower endpoint is absolute zero. And remember, that's the place, the temperature state at which colloquially the idea is that average kinetic energy is zero. And therefore, all motion stops. Kinetic energy is always positive. So if anything is moving, your average is going to be positive. It might not be very big, but it will be positive. But if your average is zero, that means nothing's moving. And so that's the colloquial way of referring to absolute zero. Okay, so that's down here. Everything stops. That's all the way down here. Now, experimentally, they've measured that to about negative 273 Celsius. All right, so that's absolute zero. So what Kelvin said is, let's make a scale and let's anchor it to this theoretical point where, okay, average kinetic energy goes to zero. All right, so they measure that and they figure out, okay, it's got to be at about negative 273 Celsius. Okay, and he said, let's also make the degrees the same size as a Celsius degree. Right now, it's the Kelvin scale. He didn't name it after himself, but other people honored him by naming this scale after him. And I believe the Fahrenheit scale is named after Professor Fahrenheit. And I guess there's a guy named Celsius. I'm not sure. I've never looked that up. Anyway, the Kelvin scale was proposed by him. And eventually they worked it out, and this is how it's supposed to be. So all down here at the very bottom, let's see if I can get my cursor. Right down here at the very bottom of the Celsius scale, that's the all-stop, minus 273 Celsius. Now, theoretically, that corresponds to zero on the Kelvin scale. So the conversion process from Celsius to Kelvin is simply to take your Celsius temperature and add 273. All right. So, for example, the freezing point of water, that's the middle marked temperature, that is 0 Celsius, and so it's 273 Kelvin. All right. And then boiling point of water, that's 100 Celsius. So 100 plus 273, that's 373. Okay, that's it. Way up here. Oh, I can't see my cursor. Anyway, up at the top of the pink column, 373 Kelvin. And then, okay, absolute zero, that's down here at the bottom of the Kelvin scale. Now, I should have put dots above the blue area here and the pink area to indicate that those temperature scales keep going upward. But this is the rock bottom at the bottom and 0 Kelvin. All right? So that's the basics. And as I mentioned, we're pretty much going to work Kelvin all the time. I do. But occasionally a textbook or something on the internet will be in Celsius that we want to look at or consider. And so just take that, whatever that Celsius temperature is, and add 273, and then do all the calculations with the Kelvin temperature. Now, you might have been thinking to yourself on an earlier slide, hey, Dr. B, why do you have a picture of some German guy named Max Planck? Who is that? Well, I want to talk about him because he's actually involved with the whole thermodynamic theory of matter. And that's kind of what we're talking about. And he's pretty important to it. Although he came in at the very end of it. Who is Max Planck? Why is the letter H associated with him? Well, he was a theoretical physicist in Berlin, Germany. He grew up in North Germany, Schleswig-Holstein, the capital city of Kiel. And I think he was born in 1858. And in the 1890s, he was studying thermal physics, thermodynamics and stuff. And one of the things he worked on was figuring out the electromagnetic spectrum for these special theoretical objects that they had hypothesized called black bodies. And this theoretical object is hypothetically a perfect absorber of radiation, and because of the conservation of energy, perfect absorber, also a perfect emitter of radiation. Now, those two concepts, written in English or written in German the way Planck wrote, would lead to a bunch of equations and formulas and stuff that we're not going to go into. There's a ton of calculus behind it. But we can talk about the concept of a black body. And what Planck did was he worked out the theory of black body radiation. If you've ever seen a cast iron stove, a pot-bellied stove of any kind, in a hunting cabin or even in your own house, your own home, maybe in the garage, it's frequently painted black. And the reason for that is so that it's not to hide it, but to make it an efficient emitter of radiation. Now, at the temperature that those stoves operate, they're going to put out a lot of infrared. They're not going to be so hot, usually, that they put out visible wavelengths of light. But you can get something red hot if you really stoke it up, with fuel and get it burning ultra, ultra hot. You can get it red hot or even white hot. That's even hotter. But most stoves are painted black for that reason. And I've done experiments in the lab as an undergraduate up at NYU measuring this electromagnetic spectrum. And what you do is you take or one way to do it is to take a set of ceramic tiles that are used in ovens, big ovens, and you just make a little cube of them, and you get it heated up. And you control the temperature, so you've got a thermometer in there for very high temperatures. And it's like a little furnace, but you're not melting anything, you're not cooking anything in it. It's just like a little furnace, but it has a certain color. And what you do is you measure the intensity of the light at every single wavelength that you can. So you go up from the low wavelengths to the higher wavelengths, higher and higher, and you measure energy along the way, and then, that tells you your spectrum. And that's the blackbody spectrum. The problem is, and people have done this since the 1800s, nobody could figure it out. You know, they could figure out the blackbody spectrum in limited cases for like small wavelength or really big wavelength, but nobody could knock down the entire spectrum of electromagnetic radiation, from radio waves to infrared to visible to ultraviolet to X-ray and gamma rays. Nobody could figure it out except for Max Planck. And in 1900, 115 years ago, this time of year, 115 years ago, 1900, he published several documents about his theory of blackbody radiation. And in that, he introduced the whole idea of a quantum of energy, a small bundle of energy, and he introduced his famous constant, Planck's constant, H. And that's the symbol that he has used and that people still use to this day, H, for Planck's constant. And when he did that, he successfully roped in the spectrum of electromagnetic radiation coming from these theoretical objects, which we can approximate pretty well in the lab. And when he did that, he really kicked off the quantum science revolution 115 years ago. And that marks the dividing point between classical physics, as started by Galileo and Sir Isaac Newton, and then advanced by all the other guys since then, up to about 1900. And that's when the modern theory of quantum systems was begun by Planck. And so all these concepts, all these quantum concepts, are in our future. And it was invented because of thermodynamics by Max Planck. So he's pretty important in the background of what we're doing today and for the next lecture or two. Now, here are some blackbody spectra. These are actual spectra for 5 different objects, 5 different temperatures, and I'll read them. The top one is in red. That's 5,500 Kelvin. And look how tall it is. It's the hottest object, and the energy over here in kilojoules per nanometer is largest value for the high temperature. Now this black one, the little one that's nested down here, Lindsay, below all the other ones, is 3,500 Kelvin. Now that's pretty hot for you and me. All right, that would burn your hand to, you wouldn't even want to touch that one. But it's cool enough relative to 5,500 that its spectrum is, it's not putting out as much energy at these wavelengths. So the higher up the curve is, the more energy is pouring through at that particular wavelength. All right? And then here's 3 intermediates, 5,000, 4,500, and 4,000 Kelvin. The visible band of radiation is right here in this kind of greenish band here. So kind of map that in. 5,500 peaks right in the middle of the visible band. Okay, so the top of that curve is where your visible band should go up and down from that point. Our star, the sun, is about, at its surface, about 5,800 Kelvin. And these spectra they're theoretical, but there are many stars that have these same temperatures at the surface. Our star has a temperature of about 5,800. So it would be a little bit taller than the 5,500 curve here. A little bit. 4,000 is a little bit lower. Down here, the green one. And the red one at the top is 5,500. And if we could do like a gold-colored one for the sun, it'd be a curvaceous, similar curve, but a little bit taller. And it would peak in the visible. Now, let me give you a little side note, something to think about. The most abundant color, let me rephrase that. the color from which we get the most energy from the SUN, from our star, the sun, the color from which we get most energy, is it red, orange, yellow, green, blue, indigo, or violet? Roy G. Biv, that's the order of the colors of the spectrum, from red to violet. Which color is it? It's green. The sun pours its most abundant energy into the green band. Now we get a lot of energy from red, and we get a lot from infrared too. We get a lot from ultraviolet. But the biggest energy contributors to our planet are red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. And green is the biggest. Now, what is true about the color green? I mean, you have green. I see various people with green shirts on, different shades, different hue. What in the natural world is true about the color green? The color green. Raise your hand if you know it. Chlorophyll. Plants. Right? You know what else is cool? Water. Here's something I didn't tell the morning class. Your eyeball's made of water, right? Mostly. Okay? It's got muscles and stuff, transparent cartilage and stuff, but it's a lot of water inside the interior eyeball. Guess what color of visible light goes most easily through water? Green. What color is in plants? What color powers plants? Green, chlorophyll. But now here's the kicker. You know, the most abundant energy band is the green band. Reds are good, violets are good, green is the most. Chlorophyll, plants, photosynthesis, green. But do plants produce their own light? No, they don't. They're green because they reflect sunlight. Because in a dark place, you can't tell what color it is. Matter of fact, if you're in a dark classroom, you can't tell what any color is. Usually, unless you have X-ray vision. So if a plant is only green because it reflects sunlight, what does that tell you about chlorophyll? Think about it a minute. It's absorbing everything else. It's absorbing the reds. It's absorbing the violets. And probably reflecting a little bit, but it's mostly reflecting green. It's not absorbing it. So it's not taking energy from the sun in that color band. So isn't that weird? Plant life, the most abundant life form on this planet, other than bugs maybe, I don't know. Probably plant life's more abundant. It reflects the most abundant energy source on our planet, the green light from the sun. And yet, it has learned to... what is that? I don't even know. I mean, I don't even know what that is. The most abundant energy form, the one that goes through our eyeball the best, the one that makes plants green, is the very color it doesn't seem to use. What is that? So who's in here is a biology or has had biology? Oh, there's a lot of slackers in here. Well, if you have, did they ever talk about that in biology, the color green? Why does it reflect green and not, I mean, I know it's because of the chromium in the chromophore. Did you know that, here's something else that's interesting. I don't even know how to think about this. The red blood, you have red blood cells, right? I'm getting all excited. My earphone's coming off here. You have red blood cells, right? Because of iron, hemoglobin. The hemoglobin molecule, right in the middle of it is an iron atom. Exact same place in chlorophyll. I think is it chromium, or what? I think it's chromium. I can't remember exactly. It's the same structure, but it's a different metal, and it makes it green. And it's the other energy. It's incredible the way that all these molecules, they work together. They're different, and yet they're working together. And there's a lot of cool things to think about. Blackbody radiation. So Planck, he started it, and we're still working on it. And it's a lot to think about. Now, I want to talk about some other everyday temperatures. Here's one. Just so you have a couple ballpark figures on the Kelvin scale. So if somebody says, yeah, room temperature, you just think about 290 or so. All right. Human body, 98.6 Fahrenheit. That's about 310 Kelvin. Now, in chemistry class and in the chemistry lab, they have something called standard temperature and pressure. So they try to do a lot of their calibrations of their chemical reactions and stuff at standard temperature and pressure. Okay, standard temperature is 0 Celsius, therefore 273, the freezing point of water. And the reason they like that is because it's easy. Ice is easy to make, and it's abundant. So it's easy to keep stuff at the temperature of ice water. Ice water is 0 Celsius, 273 Kelvin. That's easy to maintain. Just keep adding ice, and it will stay at that temperature. You know, if you run out of ice, go down the hole of the ice machine, get some more. Easy to get. All right, so that's why they do that. The top of Mount Everest on a cold night, yeah, about 238. I don't think anybody spends the night up there. But if you're in an airplane about that altitude, airplanes go even higher than Mount Everest. So they're even colder. If you're in a jet at night at high altitude, 40,000 feet, you're even colder than this, Kelvin-wise. So that's just a few everyday things. You could look up some other ones. And the way you do it is just look up the Celsius temperature and add 273. Now, I want to do a couple clicker questions with you. Multiple choice. Let's get those going. Oh, I better pause my... oh, gosh. All right, here we go. Question 1, simple conversion, Celsius to Kelvin. Frequency BB. Caitlin, did you want to talk to me after class? All right. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, pretty good. 96% of you got this correct. 417. Yeah, just here's your, if you didn't get it right, Just add 273 to 144. Don't subtract it. Subtracting gets you negative 129. That's no good. And here's another way to think about it. Kelvin temperature is only positive. You never have negative Kelvin temperatures. Now the next one is a public information survey kind of a thing. So answer to the best of your ability, and every answer will be counted correctly. But there's only one answer that's correct, so try to get that. Here's question 2. Ammonia. The hard part about having closed captioning in lecture is I can't use a lot of unusual words. I can't make up words on the fly. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Uh-oh. We got some splaining to do here. Correct answer is pungent odor. Most of you selected that, but some of you selected that it never evaporates and that it's lighter than water. Okay, those are not correct. I'll count them correct, though. I mean, it's because it's a survey type question. But the thing about ammonia is, if you're in a hot room, so here's some notes about ammonia and about gas in general. Ammonia is a gas, or it evaporates into a gas from liquid ammonia. And you smell it because it comes into your nostril as a gas, as a molecule undergoing random motions in the atmosphere. So the air in the room, if it's not pure ammonia, I mean, you would die. You'd be asphyxiated. You'd die of lack of oxygen. Oxygen asphyxia. But there's enough in there that you can tell it's there, and the closer you are to the bottle, or the hotter the day, if you're in a warm room, the smell will diffuse as a gas through the room more rapidly. And if it's really cold, it'll take its sweet time. It'll go much more slowly. If it's really, really cold, it'll freeze. You can freeze ammonia. I'm sure there's probably tons of refrigerators in Orlando that are cold enough, if you crank them up, can get down and freeze ammonia. And this, what you observe, the speed at which you smell ammonia, depending on the temperature of the room, hot versus cold, that is an example of how temperature, in this case the temperature of the room, correlates to the average speed and the average kinetic energy of the gas molecules. So the ammonia molecules are going to assume the same temperature rapidly as the air in the room. So if the air in the room is hot, the ammonia molecules will be the same temperature and have a lot more kinetic energy than if the room were colder. And if they have low kinetic energy. That means they don't get to you as fast. Here's another way to put it. If you were in a fairly small room, but the thermostat was up to like 90, so you're in there sweating, and you open up a bottle of ammonia, you might smell the ammonia in about a minute and a half. If the room is, like a broom closet, or where they store cleaning supplies. But if the room is really cold, it might take 20 minutes for you to start smelling the ammonia. All right? So that's kind of what we're talking about here. Now, to review, there's this whole idea of the kinetic theory of gas. There's zillions of those molecules. They fill the room with its odor if the concentration is strong enough. And because it's a gas, it's going through all these random motions, all different kinetic energy states, zillions of different kinetic energy states available by temperature, and only one kinetic energy value is the average. So the whole idea of the kinetic theory of gas is if it's a moderately reasonable gas that obeys F equals ma, you can use trig, you can use calculus, and you can use stats to figure out an average kinetic energy. It's challenging, but it can be done. And through that, they have established this general principle. Statement 4, you could write down as a formula that the temperature is proportional to the average kinetic energy. I had a student in office hours yesterday asking me about formulas, and I said, no, you don't want to think in terms of equations. You want to think in terms of concepts and what is actually happening. And so if you know that the average kinetic energy is affected by the temperature, you can write this sentence down, and then after you write the sentence down with the correct concepts, then you can maybe start thinking about an equation. Now, I'm not going to write that equation down. It's simply temperature equals a constant times average kinetic energy. But the concept is enough, even without the formula. Now, I want to talk some more about heat, specifically heat transport. And if you have read Chapter 5, Section 4 about heat, there's a lovely description of it, very cogent, very compact and concise. It's lovely. Now, this particular picture, go ahead and make a note. Dr. B has an image of what do you call these guys? A fire breather? Raise your hand if you've ever done this. You have? No, you haven't? Okay. Raise your hand if you never want to do this. That would be me. Okay. Raise your hand if you've ever seen it in real life. Okay. I've never seen it in real life. I've only seen pictures. The cool thing about this is this particular image and some of the other images we're going to use of fire breathers, they show all three modes of heat transport. So let's get to it. There are three modes. The first one is called conduction. Now, conduction is basically some kind of physical contact of two objects that are not in thermal equilibrium. So a hot object and a cold object. The heat will flow into the cooler object relatively easily. And when it does that, that kinetic energy raises the temperature because it raises the average of the kinetic energy of the cooler object. All right? And so, if it raises the temperature, it might start a chemical reaction, ignition. And that's what this guy has done. This picture here, you see him, that fireball is out there, kind of floating away from him. But if you look in his right hand, you can see a little torch, kind of a little mini torch. And if you think about it, he's got to do that. He's got to have something to set the kerosene on fire to get it to ignition temperature. because he doesn't actually have fire in his mouth. He's got liquid kerosene in his mouth, and he spurts it out as a stream of droplets, and then he touches it with that little hand torch that he's got, and that starts the fireball going. And he puts it close to his mouth, but he doesn't put it in his mouth, because then he'd start a fire in his mouth. You don't want to do that. That'd kill him. But I wouldn't even want to put kerosene in my mouth to start with, but I guess those guys do it. I guess you get used to it. But he's got to touch it off. So that's from the torch to the liquid droplets of kerosene. Raise the temperature of those droplets, they will ignite. Or the kerosene fumes will ignite. The kerosene vapor, or whatever it is he's using. Okay, so that's an example of conduction in this picture. A counterexample of conduction is an insulator. And if you read your highlights in the e-text last night, you saw that I put a lot of notes about insulators. If you have a goose down jacket, or a sleeping bag maybe, or if you have a fleece jacket, or a nice fleece blanket, they work because they trap air. And air is a really good insulator. Here's an example of how you can tell that. If you have air at 98 degrees, that's body temperature, right? It feels hot, but if you stick your toe in water, or you stick your foot in water that's 98.6 degrees, it's going to feel a lot hotter, because the water conducts heat away from your body, right? Or you can think about it as cold air. Here's a great example. If the temperature here is 70 degrees, if the air temperature is 70 degrees, you could walk around in shirt sleeves. Most people, unless you're from like Miami, then you'd have to put on your parkas and everything like that. But for people up here in Orlando, 70 degrees, yeah, you could maybe walk around in a shirt or maybe a sweatshirt or so, but nothing fancy. But then if you try to swim in 70-degree water, you're going to freeze your you-know-what off. You're going to jump right out. It's too cold. All right? Unless you're really a brute. We used to, when I was a kid, we used to go to, my parents would ship me off to summer camp with my big brother up in Maine. And we went to this beach sometimes that the water was 55 degrees in the summer, in the hottest part of the summer. And we would go swimming there, and you go in there for like 2 minutes, and you come out, you're completely exhausted. Your skin is all flushed red and everything. That's amazing. Things we used to do when we were kids. Anyways, that's conduction. So air is a poor conductor. It's an insulator. Water is a pretty good conductor, and it will cool you off. You'll feel it. Second mode of heat transport is convection, and this is the bulk transport or the bulk motion of big blobs, big fireballs of hot stuff, higher temperature gas or higher temperature liquid, any kind of a fluid. So if conduction is not really rapid, you can get bulk motion because hotter stuff is usually less dense. So, if you take something out of the oven that's wrapped in aluminum foil, the aluminum foil will be hot, the same temperature as the oven, but then when you touch it, it cools off so rapidly that, you can usually, unless it's filled with liquid, so if you take out a tray that's filled with liquid, gravy or something like that, and it's hot, it's still in contact with the aluminum. But if you have something in the oven that's dry, and you take it out, you can just unwrap it and then put it on the plate, stuff like that. So the aluminum is pretty efficient at conducting. All right? So you won't get any convection in a system like that. But if the conduction is not rapid, you can get buoyancy effects. So that big blob of hot gas in this picture rising up out of that guy's gullet, that fire breather, if you look at it, it's a snapshot, right? But you know that if you've ever seen it on TV or you've seen it in person, that fireball rises up into the air pretty rapidly. I mean, that's part of the coolness of it, you know, and that's convection. And it's because of the buoyancy of the hot fluid in a bulk, you know, contained area surrounded by a cooler fluid. So just, you know, so this is an example. Here's another example. The mantle of the Earth underneath Yellowstone National Park, there's a big plume of heat working up from the very core of the Earth. Question? Good. It's called the Yellowstone mantle plume. There's another similar plume underneath the Hawaiian Islands. And those two plumes, that's why there's volcanoes in Hawaii, and that's why Yellowstone has a lot of geysers. And in fact, Yellowstone, they think, is actually a super volcano that, unlike Hawaii, those things are erupting all the time, you know, very frequently. But Yellowstone only erupts every few 100,000 years, they say. And it could erupt any time now. Hopefully not soon. Hopefully not tomorrow. If Yellowstone ever blows, then the USA is toast. Sorry. It's going to knock out everywhere from California all the way to Chicago and New Orleans, maybe more. And that's basically half our country. Alaska will escape, and maybe us guys down here in Florida. But we'll all be affected by it. No, we won't be affected by the blast. It's a big catastrophe. Anyways, it's a big blob of heat working its way. Nobody knows why, but there's a few mantle plumes around the Earth, Hawaiian Islands, Yellowstone, and it's convection. Let me go back to that. I want to give you another couple examples of convection. Example F. Thunderstorm. Every time you see a thundercloud, you're looking at a huge convection system. The air heats up, and the water vapor in the air rises with it. And it gets to a certain altitude, the water vapor will start to condense. It will form small droplets. Those small droplets reflect light from the sun, all the colors of the sun, and they look like white, fluffy clouds, if there's enough of them. But meanwhile, everything else is still upwelling. So they're forming droplets, but also everything that doesn't form droplets immediately will keep going upward, upward, upward. And then the top of the thunderhead, the anvil top, is really flat. And that's the elevation at which the stuff gets so cold it starts to crystallize. Now, if stuff starts falling from there, you get hail. Maybe, if conditions are right. It might turn to water on the way down. But that's a huge convection system. I love looking at thunderclouds, thunderstorms. I mean, I don't like being out in them, but I like looking at them from a distance. Example G of convection. And hopefully this makes sense to you. Hurricanes. A hurricane is actually a conduction and convection system. It's primarily the atmosphere is convecting, huge numbers of well-organized thunderstorms, but it gets its heat energy from the ocean itself, and that's by conduction. So the air is in contact with the ocean, and the ocean is warm enough to heat up the air and start the whole convection process. Did you know that a hurricane, when it goes through from point A to point B across the ocean, it leaves behind a trail of cooler water that they can observe from space. They can measure. They can see it. It's like a trail. Like 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 you're walking through snow. And for those of you from Florida, snow is this white stuff that comes from water when it gets really cold. Anyways, you walk through snow, you leave footprints in the snow, or sand. You leave footprints in the sand. And a hurricane leaves footprints through the ocean, just slightly different temperature, slightly lower temperature, because it takes a significant amount of energy out of that surface water. The first, 100 feet or 200 feet of water goes into forming the hurricane. And so it leaves that water cooler. It's kind of cool. Kind of cool. It is cool. All right. Third mode, radiation. So when I talk about radiation, I mean electromagnetic radiation. Now, the weakest form of electromagnetic radiation, so you can write down weakest radiation, is radio frequency. So when you're listening to 580 ESPN AM, that's pretty weak. And then FM, WDBO 96.5, FM, that's a little bit higher frequency, a little bit higher energy, but still radio. Above radio is microwave. Above microwave is infrared. Above infrared is Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Above violet is ultraviolet, so that's even more high energy than the visible. Above ultraviolet is X-rays. And those are the ones that have so much energy they can penetrate your skin but not your bones. And that's why they make good X-ray photographs. And above X-rays is gamma rays. Really, 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 really high energy radiation. Sunlight from the sun, all the photons, all the reds, the greens, the violets, the infrared, the ultraviolet, even X-rays leave the surface of the sun heading for Earth. They each carry momentum and kinetic energy to us. Okay, so it can be visible light or any other kind of radiation. And the sun produces a lot of infrared and it produces a lot of ultraviolet as well. Not so much X-rays, but it does produce X-rays. And our atmosphere shields us from a lot of the harmful radiation. Now, if a material, so that sunlight comes through space, and if it hits a spacecraft, then depending on the material, it might absorb it or it might let the light pass through. Now, glass will let a lot of light pass through. And so it's transparent, translucent. So it won't absorb a lot of energy, but it will still get warm. I mean, you'll be able to touch it. It'll be warm, a pane of glass in the sun. But the same mass of opaque material will be even hotter. So another example, skin cells. When they absorb ultraviolet, that energy goes into a chemical reaction that ends up giving you sunburn. Right? You feel it. Even astronauts that are up on the moon, the Apollo astronauts, they had to have extensive shielding from sunlight because there's no atmosphere on the moon. So, and this distance from the sun, if there's no atmosphere to absorb or reflect the sunlight, you're getting a lot of energy. Here's the rough amount of energy per second that comes to Earth from the sun. So 1,370 joules per second for every square meter facing the sun. So if you have a square meter would be this if you took this table here where I'm sitting and you convert it into a solar energy panel, this tall and this wide, that'd be about 2 square meters. Okay, so think about half this desk, half this table, a solar panel, is absorbing 1,370 joules every second. If it's facing the sun, facing directly to the sun. So here in Orlando, we'd have to kind of tilt it so it's facing directly into the sun. Okay? Down at the equator, they'd have to tilt it directly. It'd have to be tilted straight overhead to get the energy, because the sun is always overhead at the equator. On the night side of Earth, so like right now in the Philippine Islands, China, it's night. Okay, so they won't be getting, so no matter what they tilt their solar cell, if you're on that side of the Earth, you don't get anything from the sun. But if you're on this side of the sun and you tilt it so it's face on to the sun, 1,370 joules per second per square meter. That's a lot. Now, here's a side note, a couple side notes to share with you. Spacecraft, satellites and stuff, a lot of times they're covered with this kind of silvery stuff. It looks like really, really shiny aluminum foil. It's called mylar. It's really light and it's really reflective and shiny. And the reason they put that on a lot of spacecraft is because they don't want the sun to cook their spacecraft. NASA had a problem back in the 80s, I guess. Late 70s, early 80s. They had a floating space station, Skylab, that it wouldn't unfold its solar energy panels. And so it was taking a lot of solar radiation directly, and it was overheating. So they had to try to fix it. It was a real mess. So a lot of times a spacecraft will want to defeat that. Same thing with the Apollo astronauts. One of the cool things they have is even their face visor. They have to look through it to see where they're going, but it's coated with a very, very thin layer of gold, they say, to defeat the solar heat gain from the sun. And the reason it's especially needful on the moon, but anywhere in space really, is because on the moon there's no atmosphere. The space shuttle is actually, I think there's a little bit of atmosphere up where the space shuttle is. Not a whole lot, but it's not a perfect vacuum. The moon is pretty close to a perfect vacuum. No atmosphere. Now, compare that to this object here. This is a solar roof collector, a solar energy collector for the roof of your house. You want that to gain. So you optimize this baby to gain solar energy, solar heat gain. Heat your water up, so you can take a hot shower, or so you can heat up your pool, et cetera, or your hot tub. So there's all kinds of applications. Here's another one. SR71 Blackbird, famous reconnaissance plane, supposedly in retirement, but who knows? They'll probably take it out whenever they need it. Wonderful airplane, and the cockpit of that supposedly was coated in a thin layer of gold because they're so far up in the atmosphere that those guys are exposed to a lot of ultraviolet. Matter of fact, if you're up on top of Mount Everest, or even in Montana, 10,000 feet, you're going to be exposed to a lot of ultraviolet. You're going to get really bad sunburn. If you don't cover up or have SPF, 50 or something, your fabrics will degrade. All your synthetic fabrics will degrade in sunlight like that. Another cool thing about the SR71 Blackbird is the leading edges of the wings. It could fly at like Mach 4 or something like that. Nobody knows, or nobody's saying their top speed. But it would fly so fast that the leading edge would get red hot. And you could observe that from space, observe that if they're up in the atmosphere and operating at night. And I was able to actually see that once out in Montana. So let's try to get a handle now on the stuff you're going to need for your homework. That guy just left. He's not going to get it. And that is, how do things heat up? What is it that objects have that causes them to be easy to heat up or tough to heat up? First thing we need to do is define the thermal unit called the calorie. All right? The calorie is a unit of energy. You can use it for energy calculations of any kind. So if you want to calculate kinetic energy of a baseball in calories, you are welcome to do that. Usually, however, it's used in thermal applications, thermal systems, by tradition. A calorie is defined in the following way. It is the amount of energy that is required to heat up 1 gram of liquid water from 14.5 Celsius to 15.5 Celsius. That's it. And it's considered a metric system unit of energy. And so is a joule. But calories is also, and it's defined in terms of what is required to heat up water. 1 gram. So 1 gram of water. And the guy that kind of figured all this stuff out is a very, very famous guy, a British scientist named James Prescott Joule. In web courses, there's a new blurb page with some extra readings. The last 3 extra readings on that blurb page concern James Prescott Joule and William Thomson, Lord Kelvin, and another guy named John Dalton, who was a big student of molecules and atoms and was actually a tutor for 2 years for James Prescott Joule. So those 3 guys, there's little biographical blurbs I'd like you to read this weekend, and you'll have some homework about that. What he did, what James Prescott Joule did, he said, all right, I'm going to try to convert kinetic energy from GPE of this falling weight over here. See that little, over here in the diagram on the far right? There's a weight tied to a string. The weight can fall downward. If it falls downward, it pulls the string over the pulley. And then the pulley, the string pulls that spindle, and the spindle spins that axle, and the axle is attached to those paddles in the water, and the paddles spin in the water. When the weight drops to the floor, it stops. The paddles stop. The water has received energy. And then you measure the temperature of the water. So here's your delta Y. Go ahead and add this to your diagram. You measure the amount of delta Y. So if you know the mass of your weight, 20 grams or 200 grams or whatever it happens to be, and then, so that's your M, and then your G is 9.8, of course, and then your delta Y is 20 centimeters or 1.2 meters, whatever you design it to be. That tells you how much energy goes into the paddles. So they get a lot of kinetic energy from this falling weight. All right. When the weight stops, the paddles stop. When the paddles stop, all the energy is in the water. Then you measure the temperature. So for every joule of GPE, he was able to map out how many degrees, and I don't know if he was working in Celsius or not, maybe Fahrenheit, but you could figure out, if you do this experiment, for every joule of drop energy, how many, and for like 10 grams of water or 100 grams of water or whatever amount of water, how much does it raise the temperature? And he was able to figure it out. Here's what it is. For every 4.184 joules of GPE, every 4.184 joules of drop energy, he was able to get 1 gram of water to rise by 1 Celsius degree. So gram for gram, Celsius degree for Celsius degree, this is what it takes, 4.184 joules, if it's liquid water. Okay, so he was working with water. Theoretically, and there's an interesting story about this, the water at the bottom of a waterfall, like Niagara Falls or something, is going to be a little bit warmer than the water at the top of the waterfalls. So it's because it receives a lot of mg delta y by the time it gets down to the bottom. So it's measurable, apparently. And Joule was able to measure that. Another calorie concept that we need to know the basics of, and that's the food calorie. A food calorie is 1,000 of the thermodynamic calories. So a food calorie has a capital C. And the thermodynamic calorie, 1 gram of water, 1 Celsius degree, that's a little c. 1,000 of the little ones equals 1 food calorie. So think about this. A food calorie, no matter what kind of calorie, that's 4,184 joules. 1,000 of these, thermodynamic calories. That's a lot of energy from food. You know how they figure out the calories content of food? They burn it. Now, a couple more concepts before we dismiss. So we stir up water, kinetic energy, and it increases the temperature of the water. And so you're going to have two things that are not at thermal equilibrium. One's going to be warmer than the other. So for instance, object X is a lower temperature than object Y or substance Y. And if that is true, energy flows into X and out of Y. And here's kind of the submicroscopic view of how that works. Faster molecules are going to migrate to X more rapidly than they migrate to Y. Why is that? Well, substance Y has a lot more because it has a higher temperature, higher average. So there's a lot more fast molecules in substance Y. They get over to X faster. Now, substance X is going to have some fast movers, but not as many. Why is that? Because it has a lower temperature. Its average kinetic energy is lower. So it's going to have some fast movers, but they're not going to be as fast. So draw a big arrow in red for the fast movers, and lots of them, from Y heading over to X. Now that's going to raise the average of X. But meanwhile, X is going to send some high energy guys over, but they're not as many. So make that a little bit less bold of an arrow. So it's kind of pokey, kind of weenie-ish. So that's the preferential, and it only has to do with average temperature. Average kinetic energy. That's it. If the average kinetic energy of Y is higher than the average kinetic energy in X, this is what's going to happen. Eventually, though, they're going to balance out. The temperatures will be equal. And now you can write down two different arrows, both the same size, these gold arrows. These signify that, you're still swapping kinetic energy from substance to substance, but in the same amounts. So X gets from Y the same amount that Y gets from X. So that's all right. Eventually that's going to happen, and when it does, you're at thermal equilibrium. All right? Now, before we dismiss, I want to tell you a couple things for the weekend. Finish reading chapter 5. You start reading chapter 6. Skim that if you like. There'll be some homework available by lunchtime tomorrow, due Tuesday. And we'll finish up heat concepts on Tuesday. You're dismissed.